Today we're going to start section 1.1, and we're going to be taking a look in this first chapter at problem solving in general. So today we're going to talk about some problem solving strategies and how to think about solving problems. For the most part, I'm not asking you to write down a step-by-step. This is step 1 in solving problem. This is step 2. This is step 3. Because whether you're realizing it or not, your brain's going through all these steps each time anyway, with the potential exception of the last one, and that's one we should be a little bit more careful about. But to start with, when we're looking at solving problems, the first thing to make sure that we're understanding is the actual problem, to figure out what they're talking about. So some questions that sometimes we ask ourselves is, can the problem be stated differently? What is to be found or what is needed? What are the unknown things? What information is obtained from the problem? What am I given? And then what is missing or maybe not needed? And those do come up sometimes even in book problems. But they really come up in real life problems all the time. And so we're constantly in a state of solving problems, whether it's mathematical or not. You do it all the time. The first thing you do after you've figured out what it is that you're being asked is to figure out how you're going to go forward. Devise a plan. The following is a non-exhaustive, that means it doesn't include everything, list of strategies. So sometimes we look for a pattern. We might examine related problems. You guys have done that before when you go back and you look at the examples in the book when they do that, right? Or the examples the teacher gave you. Examine a simpler or special case. Sometimes if there's a big problem, if we can narrow it down into a smaller problem and then generalize what happened, that's a good strategy. Tables and lists. Are any of you list makers? That's where I am. I really like making lists. I always have lists. I like marking things off lists. Even things that weren't originally on the list, and I add them to the list so that I can mark them off. Yeah, that's me. Identify a sub-goal. Sometimes if we can get to one place and figure out where, if I can only get to here, then I know I can solve the problem, and that simplifies what I have to do, because I know what to do after that. So identifying a sub-goal. Make a diagram. Even if you're not good at art, you can make diagrams. I'm terrible at art. I have at least 3 of my children who would consider themselves artists. I don't. But sometimes it's still helpful to draw a diagram. Guess and check is totally valid. Probably nobody's ever told you that before. But it is, as long as you're being reasonable in how you guess and check things. Random guessing and checking is usually not a very good strategy, but organized and structured guessing is probably a really good way to go on some things. Working backwards. Have you ever looked at the back of the book and said, oh, they got 38. How did they get that? You've worked backwards then. Working backwards can be very helpful. And then sometimes, although in very extreme situations, write an equation is a good way to go. You have most likely and most recently been in the make an equation for everything mentality. The reality is that the majority of what we're doing in this class is geared toward our younger grades. So those of you who are teaching up to about 4th grade, this class is totally for you. So we're not going to make equations for the most part. It's not going to be a real common thing we're going to do. We're going to be working with other strategies to see how you would think about this from a younger child's perspective. So we're not going to do a lot of equations. If you use an equation, that's fine. It's not going to be a problem. It's just something that I want you to be aware that most of the time that's not going to be the strategy I'm going to go to. Okay? All right, once you decide I'm going to use this strategy, you got to do it. So you carry out the plan. So you implement the strategy from step 2, doing any actions, computations. Be careful to the language that's being used. If something asks you for area and the answer you give them is the dimensions of the soccer field, you didn't answer the question, right? So being careful to what you're actually the language that's being used. Checking the steps along the way, either formally or intuitively. So formally means like double checking to make sure your addition added up. Intuitively means saying, does that make sense? So if you grab your calculator and you put something into your calculator and it comes out a decimal and a decimal answer doesn't make sense, that's intuitive. That means you know you did something wrong because it just doesn't make any sense. And then keeping an accurate record of your work. And then the last step is the one that people don't typically do, and usually it's not required, is to check your work. Well, if you did it right, you don't check your work, you're good to go and it didn't matter. But if you did it wrong and you don't check your work, then you've missed an opportunity to fix something that went wrong. So checking your work to see if the answer is reasonable and to see if the answer is actually accurate. Okay, so what we're going to do next is we're going to try to get through, we'll see how many we can get through, as many as we can, different ways of looking at a few problems. Okay, so there was a gentleman named Gauss. Gauss is actually a mathematician, and he goes on to do some really advanced level mathematics. And this is actually a true story of something that happened when he was young. He was in an early grade school, and his teacher gave him an assignment intending for it to take him a long time. I'm sure you would never do that to your students, would you? No, of course not. So what she asked them to do was add up the numbers from 1 to 100. So most children would go 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and they'd have a lengthy process, right? So you can see what the teacher's intending for them to do. Yep. But Gauss didn't do that, and instead he answered almost immediately. I'm so sorry for that teacher, aren't you? It didn't work out for her. So I'd like to show you what he did and what his thinking was, and then we're going to use that strategy in some future problems. Right, like we get, he's very bright. And if you think that you're never going to encounter a bright student, I feel very sorry for you because you probably will. So just recognizing that we don't all think the same way, and sometimes students go above and beyond in how they think about something is probably a reality. So I'm going to show you what he did. And here's the goal. He wants to add up the numbers from 1 to 100. I'm going to write up the first 3 and the last 3 so that you can see how the patterns of this work, so you can see what he really did. I told you I wasn't going to use equations. This is not exactly an equation. I mean, yes, I realize it has an S equals, but I kind of just put them in so that I have a place to reference this back to. Okay? This is the sum. S just means sum. Okay? So he's adding up the numbers from 1 to 100. So what I'd like for you to do is I'd like for you to add those numbers underneath reversed. So if we start out by putting the 100 underneath the 1, and the 99 underneath the 2, and the 98 underneath the 3, and we continue on to the 98 and do it continuing in reverse, right? So this is 3, and then 2, and then 1. And I'd like you to add like you would add if you were in grade school, early grade schools, right? We add vertically down a list of numbers. So what is 1 plus 100? 101. And what is 2 plus 99? 101. And what is 3 plus 98? 101. And lo and behold, they're all 101. There's a bunch of 101s. They're all the same number added, right? Now, this sum, 101 plus 101 plus 101, it isn't the original amount that I had. What is it? It's what? I can't hear you. Who's talking? I don't even know. Like this is not S, right? What is it? So if I added something to itself, what is it? It should be double, right? If you add something to itself, you double it. I make a pie, you make a pie, we have 2 pies, right? Yeah, right? It's just double what we started with. So we're going to call it 2s or twice s. You could use words if you don't want to use symbols. But it's twice as much as what we started with. Now here's the cool thing. Adding up the numbers 101 plus 101 plus 101 is a lot easier than adding 1 plus 2 plus 3. Because the numbers don't change each addition step, right? Yeah. And in fact, there's something that you learn. We usually learn it these days in about the end of 2nd grade, but all through 3rd grade, and then they hit it again in 4th grade. And if you're like my 4th graders, maybe you still don't quite have it down. And the subject is called multiplication. Multiplication is repeatedly adding something together, right? Like 6 times 5 is 6 5 times. It's 6 plus 6 plus 5 times. That's what multiplication is. It's repeated addition. So this is repeated addition, right? I got a bunch of 101s added together. Well, it'd be a lot easier to multiply these than to add them together. Yes? If I just knew how many of these there are. How many are there? You're close. There's 100. Because they were the numbers from 1 to 100 when I started. There's 100 of these. Is everybody good with that? Okay. There's 100 of these numbers that have been added together. So the reality is I don't need to add 101 plus 101 plus 101 100 times. I could multiply it by 100. I've still got double what I need. This is not my original value, my original sum. It's twice as much as what I want it to be. But what is 100 times 101? Somebody tell me. 10,100, that's right. But that's double what I want it to be. So how do I find out what it actually was supposed to be originally before I doubled it? I divide it by 2, I half it. We'll write it divide by 2 like that. So my original sum is actually going to be 5,050. That's where you were getting your 50 from before, by the way. Yeah, it's 50-50. So the cool thing is, there's really nothing special about the numbers from 1 to 100 here. There's really nothing special about the fact that we have all of them, 1 plus 2 plus 3 plus 4. Like we could skip numbers. But this method, this strategy actually works in more than just this very specific situation. For example, take a look at example number 2. I'm adding some numbers together, right? Yep. They're not the numbers from 1 to 100, but I could use a similar strategy. And so I could start out the same way. This has got an S. S just stands for sum. And I already have these digits. I don't know why I'm rewriting it. Apparently, I just like to write today. I do want to rewrite the last 3 digits, though. I only have 2 of them written here. So I have 145, 146, and 147. So what did I do first if you look back at that other problem? Yeah. So I switched the order around, right? What I really did is I added something to itself. I just switched the order around so that the numbers pair up nicely. So I'm going to add it to itself. So I'm adding to this 147, 146, 145, 38, 37, 36. And if the strategy is going to work, it must be true that each of these individual additions are the same. So check them. Do they all add up vertically to the same quantity? Do they work? Yeah, I think they do. They should. What do they add up to? What are the individual sums? 183. So now I have a whole bunch of 183s. And the question becomes, well, how many 183s do I actually have? This doubled my sum, right? It doubled it because I added something to itself. But how many of these 183s are actually there?
Are we starting from 36 going to 147?
Yes, we are. We're going from 36 to 147.
111.
111. So how did you get 111?
I subtracted 147, or 36 from 147.
Okay, so here's what you did. Don't write it down just yet. There's an error, okay? But I want to show you why it happens. So you did 147 minus 36. Is that right?
Yes.
Okay, this gives you 111, and it's really close. This is really close. But think back to this other problem. If I did that over here, what would I get?
99.
I'd actually get 99. So any idea what happened when you subtracted the 36?
Are you not counting the 36?
Yes, it ends up not counting the 36. So the number you actually should subtract is the one before it. So really, instead of 36, we should be subtracting 35 here. Because you're trying to subtract things that aren't there. And if you subtract the 36, you're subtracting something that is a part of your number set. So here we really want to subtract 35, so we really have 112 terms. So there's 112 of these 183s being added together. Okay, so let me pause for a moment because you're going to have an example of this in your book that you're going to do on a group work or homework at some point, and it's going to skip numbers. That's another possibility. So if it skips numbers, what do? Well, they still add up the same way. There's no problem with our additions, okay? The problem, not the problem, but the difference comes in with when you're counting them. So let's say, for instance, we counted the numbers from 0 to 100, right, like we did on the last page, but we only had the evens. What would you have to do to figure out how many terms there are? You divide by 2. Why? Yeah, because even and odd split them into 2 equal quantities, right? What if you had multiples of 6? So you had every 6th term. You divide by 6. Okay, so there's nothing really magical about what's happening. You just need to make sure that you're actually getting the quantity of terms you have. So if it's every 3rd term, we divide by 3. And what you would divide is you divide this number right here that you just did the subtraction with. Okay, that's how that works. So that's sort of a small difference for that one. All right, so let's finish this one out. So there's 183 is our sum for each of these individuals, and there's 112 of them. And of course, that's double what I really am supposed to have. So somebody grab a calculator if you have with you. If not, we'll do something different. But what is 183 times 112?
I got 20,496.
20,000, what was it?
496.
496, good, because I didn't have that one written down yet. All right, now again, that's double what I really want, so what do I have to do? Divide by 2. So this double business is because I've added it to itself. It's not because it's every other term, okay? The every other term thing had to do with how many terms I have. The dividing by 2 here is because I added the sequence of numbers to itself. And if I divide this by 2, what do I end up with? 10,248. Okay, any questions on that? Kind of 2 examples of the same strategy. All right, we will pick up next time with the simpler case example and finish out section 1.1 on Wednesday.